Sagittarius A, the silent giant we are all orbiting. You're spinning, right now, 828,000 kilometers per hour. Around something you've never seen. Something 26,000 light years away, sitting in a direction you couldn't point to even if you tried. You've been doing this since before you were born. Your parents spun around it. Every person who ever lived. Every star visible on the clearest night. All of it, hundreds of billions of stars, clouds of gas larger than solar systems, planets we'll never name. Everything in our galaxy caught in vast, patient circles around the same dark center. And at that center sits something invisible, a supermassive black hole, 4 million times heavier than the sun, pulling on everything, anchoring everything. For most of human history, we didn't know it existed. Tonight, we're going to trace the story of how we found it, how we measured something we can't see, how we photographed darkness itself, and what it means to spend your entire life circling something you'll never escape. This is the story of Sagittarius A star, the thing at the middle of everything we know, the quiet center of home. Let's start. For thousands of years, people looked up and saw a river of light stretched across the night sky, faint, hazy, like milk spilled on black cloth. They didn't know what it was. Some cultures called it a road. Others saw it as a river or a bridge between worlds. Beautiful, yes. Strange, absolutely. But just light, nothing more. By the early 1900s, we'd figured out what we were looking at. A galaxy. Our galaxy, spiral-shaped, enormous beyond comprehension, and we weren't at the center of it. We were off to one side, about 2/3 of the way out from whatever the middle was. We assumed there had to be a middle, some dense core where stars clustered together more tightly, a bright, crowded region where starlight pooled. But we thought it was just more stars, closer together, brighter maybe, nothing unusual. The problem was, we couldn't see it. Between us and the center of the galaxy, there are massive clouds, dust and gas stretching across thousands of light years, thicker than fog, denser than smoke, completely opaque to normal light. When you point a regular telescope toward the center of the Milky Way, you see nothing, just darkness, a wall of black where the brightest part of the galaxy should be. For centuries, the heart of our own galaxy was hidden from us. We lived inside it, spun around it, but couldn't see what held us. Then, in the 1970s, astronomers started using different tools. Radio telescopes. These don't look for visible light. They listen for radio waves, which pass through dust like it isn't even there. And when they aimed radio telescopes at the galactic center, they found something odd. A source, powerful, compact, unmoving, bright in radio wavelengths, but invisible to the eye. Too bright to be a single star, too small to be a cluster of stars, too concentrated to be a gas cloud. They named it Sagittarius A star after the constellation Sagittarius, where it appeared in our sky. A star because it was the strongest source in that region, the brightest thing they could detect. But what was it? Something massive had to be there, something pulling on the stars around it, bending their paths, holding them in orbit. But you can't see a black hole, not directly. Black holes don't emit light, they don't reflect it. They're invisible by definition. The only way to prove a black hole exists is to watch what it does, to see the things it pulls on, to measure the gravity it creates. And in the 1990s, two teams of astronomers decided to do exactly that. One team worked at the Keck Observatory in Hawaii, the other at the Very Large Telescope in Chile. Both aimed their instruments at the same patch of sky, the galactic center, the region around Sagittarius A star. They weren't using visible light. They used infrared cameras. Infrared light can pierce through dust the same way radio waves can. It let them see stars that normal telescopes couldn't. And they started tracking those stars, not hundreds of them, just a few dozen, the ones closest to Sagittarius A star. Year after year, they took images, watched the stars move, measured their positions with incredible precision. And the stars moved fast. Not the slow, lazy drift you'd expect from objects so far away. These stars were whipping around something, tight orbits, elliptical paths, violent accelerations. Like planets around a sun, but far more extreme. One star became the focus of everything. A blue-white star, unremarkable except for where it was and how it moved. The teams called it S2. And S2's orbit would prove what Sagittarius A star really was. S2 completes one full orbit around Sagittarius A star every 16 years. That's fast, extraordinarily fast for something orbiting the center of a galaxy. Our Sun, for comparison, takes 230 million years to complete one orbit around the galactic center. S2 does it in 16. At the closest point in its orbit, the point called periapsis, S2 gets within 17 light-hours of Sagittarius A star. To put that in perspective, Neptune is about 4 light-hours from the Sun. S2 gets that close to a black hole. And at that distance, it accelerates hard. It reaches speeds of about 2 to 3% the speed of light, somewhere between 7,000 and 8,000 kilometers per second. Fast enough to cross the distance from Earth to the Moon in less than a minute. The scientists followed S2 for decades, image after image, year after year. They watched it sweep past the black hole in 2002, and then again in 2018, one full 16-year orbit from close pass to close pass. And the next orbit is already underway. Frame by frame, they could see S2 accelerate as it approached the black hole. They could see it slow down as it moved away. The path was perfect, smooth, predictable. Exactly what you'd expect from an object orbiting a massive point source. And then they did the math. To make a star move that fast, in an orbit that tight, there has to be something incredibly massive at the center. Something concentrated in a space smaller than Mercury's orbit around the Sun. The numbers were exact, roughly 4 million times the mass of the Sun. No star cluster could be that dense without collapsing. No cloud of gas could stay together under that kind of gravity. No normal object could hide that much mass in that little space. Only one thing fit: a supermassive black hole. By 2002, the case was closed. Sagittarius A star wasn't just a radio source, it was a black hole, our black hole. The thing we'd been orbiting our entire lives. For decades after that, we knew it was there. We could measure its mass, track the stars circling it, map the gravity it created. But we'd never seen it, not really. We'd only seen what it did, the shadows it cast, the paths it bent. In 2019, something changed. A project called the Event Horizon Telescope released the first ever image of a black hole. Not ours, a different one. A black hole called M87 star sitting at the center of a galaxy 55 million light-years away. The image showed a glowing ring, bright orange and yellow against black, and in the center, a shadow, a dark circle where no light escaped. Proof, direct visual proof, that black holes exist. And then, in May 2022, the Event Horizon Telescope released a second image. This time closer to home. Sagittarius A star. It took longer than M87 star because Sagittarius A star is harder to photograph. M87 star is massive, stable. It changes slowly over days or weeks. You can point a telescope at it and the image stays relatively consistent. Sagittarius A star is smaller and it flickers. Gas swirls around it on timescales of minutes to hours. The brightness shifts constantly. The structure changes. Like trying to photograph a child who won't sit still, except the child is also 26,000 light-years away. But the teams synchronized their data. Telescopes in Chile, Hawaii, Arizona, Mexico, Spain, and the South Pole. Multiple observatories working as one, combining signals, compensating for Earth's rotation, adjusting for atmospheric distortion. Building an image, pixel by pixel. And then they had it. A bright ring of hot gas, its light bent into a circle by gravity, wrapping around the event horizon. And in the center, a shadow. A dark silhouette where light gets captured and pulled inward, 52 microarcseconds across. Like seeing a donut on the surface of the moon from Earth, or reading a newspaper in New York from Los Angeles. For the first time, we saw it, the face of the thing we'd been orbiting our entire lives. And here's the strange part. Sagittarius A star is not a monster. It's not blazing. It's not devouring stars every night. It's not ripping the galaxy apart. Most of the time, it's quiet, starved, a giant with its mouth closed. Which means we're looking at something even stranger than a monster. We're looking at a supermassive black hole at rest. And seeing it raised questions, big ones. What does 4 million solar masses actually mean? How do you comprehend something like that? 4 million solar masses, that's 4 million stars like our sun compressed into a singularity, into a point. Let's try to put that in context. If you could somehow crush our sun down into a black hole, it would have an event horizon about 6 kilometers across. A tiny sphere, small enough to fit inside a city. Now imagine doing that 4 million times and crushing all of it into a single point. That's Sagittarius A star. The event horizon of Sagittarius A star is about 24 million kilometers across, roughly 17 suns laid side by side. Light moving at 300,000 kilometers per second crosses that diameter in about 80 seconds, a minute and 20. That's the boundary, the point of no return. And it's worth saying this clearly, the event horizon isn't a surface, it's not a shell you could touch, it's a line in space where escape stops being possible. Inside it, the rules we understand break down, not because the black hole is made of darkness or magic, but because gravity becomes so extreme that even light can't climb back out. And deeper still, our equations predict a singularity, a place where the math stops working, where physics runs out of words. Now, if you put Sagittarius A star where the sun is, the event horizon would still fit inside Mercury's orbit. But the mass would be 4 million suns. Earth, at our current distance, wouldn't be able to orbit the way it does now. To stay in a stable orbit at 1 astronomical unit, you'd need to travel at about 1/5 the speed of light, and your year would last just over 4 hours. So the horizon is small compared to the solar system, but the gravity is not. Consider the mass itself. The sun weighs about 333,000 Earths. It's so massive that its gravity holds 8 planets in orbit across billions of kilometers. Sagittarius A star is 4 million times more massive than that. That's 1.3 trillion Earths, 1,300 billion Earths. If you somehow lined up planet-sized objects, each one as massive as Earth, you'd need 1.3 trillion of them to equal Sagittarius A star's mass. Lined up edge to edge, that chain would stretch to the nearest star and back about 200 times. And yet, compared to other black holes, Sagittarius A star is small. M87 star, the black hole photographed in 2019, weighs 6.5 billion solar masses. Ton 618, one of the largest black holes ever discovered, weighs 66 billion solar masses, 16,000 times more massive than Sagittarius A star. By comparison, Sagittarius A star is tiny. But tiny is a relative term. 4 million suns, 1.3 trillion Earths, incomprehensible mass crushed into infinite density. And Sagittarius A star is 26,000 light-years away, the closest supermassive black hole to Earth. When we look at Sagittarius A star, we're not seeing it as it is right now. We are seeing it as it was 26,000 years ago. Humans were living through the last ice age, small groups, firelight, stone tools. The first cities were still 10,000 years in the future. Writing didn't exist. Agriculture hadn't begun. And photons left the black hole, traveled through dust, through spiral arms, through the quiet lanes between stars, until they finally reached our telescopes. Sagittarius A star is ancient. It likely formed in the early universe billions of years ago, when galaxies were young, still colliding, still merging. When the first stars were just beginning to light up the cosmos. Sagittarius A star was already there when our solar system formed 4.6 billion years ago, already massive, already ancient. It was there when life first appeared on Earth, when the dinosaurs lived and died, when the first humans looked up at the night sky. And it will still be there long after the sun dies, long after Earth is gone, long after every star we can see has burned out or drifted away. It's been doing the same thing the entire time, pulling, holding, anchoring. Right now, in this present moment, Sagittarius A star is doing something, pulling gas inward maybe, flaring as a cloud drifts too close, or quiet, dormant. Stars are orbiting it. S2 is somewhere in its 16-year path. Other stars are accelerating toward their closest approach or drifting away. The event horizon is there. The ring of light is glowing. Something is happening, but we can't see it. The light that would show us Sagittarius A star as it is right now, in this exact moment, won't reach Earth for 26,000 years. Think about that. 26,000 years from now. Modern humans appeared roughly 300,000 years ago. 26,000 years is nearly 1/10 of the entire span of human existence. In 26,000 years, human civilization might be unrecognizable. We might have spread across the galaxy, or destroyed ourselves, or evolved into something we wouldn't recognize as human. Earth's climate will have shifted, continents will have drifted slightly, species will have gone extinct, new ones will have appeared. The stars in the night sky will have moved to different positions. And only then, 26,000 years from now, will the light from today's Sagittarius A star finally arrive. Only then will observers, if there are any, see what Sagittarius A star looked like in the year 2026. We are always watching the past, never the present. The black hole we photographed in 2022, that was Sagittarius A star as it existed 26,000 years ago. S2's orbit that we've been tracking since the 1990s, we are watching events that happened 26,000 years before we saw them. Everything we know about Sagittarius A star, every measurement, every observation, every image, ancient history. And there's no way around it. Light has a speed limit, information has a speed limit. We are separated from Sagittarius A star not just by distance, but by time itself, a 26,000-year gulf we can never cross. What is Sagittarius A star like right now? We can't know, not for 26,000 years. All we have is the past, always the past. But the past is enough to tell us what Sagittarius A star does. Sagittarius A star doesn't hold the entire Milky Way together by itself. The galaxy is bound by all of its mass, stars, gas, and dark matter added together. But Sagittarius A star rules the inner heart of it. Near the core, its gravity dominates. It sets the rhythm of the closest stars. It anchors the very center we measure everything from. And in that sense, quietly, relentlessly, it is the dark landmark at the center of home. We orbit at 230 kilometers per second, fast enough to circle the Earth in about 3 minutes. But the galactic center is so far away that one complete orbit takes about 230 million years. The last time our solar system was in this position in its orbit, dinosaurs hadn't appeared yet. The next time we come back around to this spot, 230 million years from now, Earth might be unrecognizable or gone. Stars closer to Sagittarius A star orbit faster. S2 completes an orbit in 16 years. S62, another tracked star, has been reported to have one of the shortest known orbits, just 9.9 years, screaming around the black hole at nearly 10% the speed of light at its closest approach. Farther out, stars take thousands of years per orbit. And at the edges of the galaxy, 70,000 or 80,000 light-years from the center, stars crawl through their orbits over hundreds of millions of years. Some stars have been circling Sagittarius A star for billions of years. They'll keep circling for billions more. Generations of stars, born and dying, all held in orbit by the same invisible anchor. Sagittarius A star doesn't care, it doesn't hurry, it doesn't rest. It's patient, invisible, silent, but absolute. Every star near the core bends to it, every orbit, every trajectory, every motion shaped by its gravity. You can't negotiate with it, you can't escape it. We are bound to it. The quiet center of everything. Right now, somewhere near the constellation Sagittarius, there's a black hole. You can't see it with your eyes. You can't point to it in the sky and say, there. But it's there. And you've been circling it your entire life. So have your parents. So has every generation before you. So has every star you've ever seen. All of it held by something we couldn't even photograph until 2022. Something we still can't see as it is, only as it was 26,000 years ago. The dark heart of the Milky Way. Not the most massive black hole in the universe, not the farthest, not the brightest, but ours, the center of home. When you think about black holes, you probably think about destruction, violent explosions, stars being ripped apart, matter spiraling inward at impossible speeds, heating up until it glows brighter than entire galaxies. And that happens, just not here, not with Sagittarius A star. Sagittarius A star is starving. Most supermassive black holes at the centers of galaxies are fed by a constant stream of gas and dust. Matter falls in, heats up, releases enormous amounts of energy as it spirals toward the event horizon. These are called active galactic nuclei, quasars, blazars, some of the brightest objects in the universe. But Sagittarius A star is quiet, it barely feeds at all. Occasionally, a cloud of gas drifts too close, or a star gets torn apart by tidal forces, and for a brief time, Sagittarius A star flares, brightens, releases a burst of X-rays or radio waves. But most of the time, it sits there, dormant, waiting. The region around it is nearly empty, no thick disk of glowing matter, no jets of plasma shooting out at relativistic speeds, just a thin trickle of gas, barely enough to notice. Scientists estimate that Sagittarius A star accretes, meaning consumes, only about 1,000th of an Earth mass per year. That sounds like a lot, but for a black hole 4 million times the mass of the Sun, it's nothing, a drop in an ocean. If you could somehow transport Sagittarius A star to the center of a more active galaxy, surrounded by dense clouds of gas and dust, it would become a monster, a quasar, visible across the universe. But here in the Milky Way, it's quiet. Some scientists think Sagittarius A star used to be more active. Billions of years ago, when the galaxy was younger and more chaotic, it might have fed more regularly, grown faster, shone brighter. Evidence for this comes from something called the Fermi bubbles, two enormous lobes of gamma-ray-emitting gas, extending above and below the galactic center for about 25,000 light-years in each direction. These bubbles might be the remnants of a massive outburst from Sagittarius A star millions of years ago, a time when it consumed something large, a giant gas cloud maybe, or another black hole. The bubbles are still there, glowing faintly, a reminder that Sagittarius A star wasn't always this quiet. But today, it sleeps. And that's strange when you think about it. We live in a galaxy with a supermassive black hole at the center, and it barely does anything. Other galaxies aren't so lucky. In some galaxies, the central black hole is so active, so violent, that it prevents new stars from forming. The energy it releases heats the surrounding gas so much that it can't collapse and ignite. Entire galaxies, sterile because their black hole won't stop feeding. We got lucky. Sagittarius A star is gentle. It holds us without destroying us. And because it's so quiet, we can study it, get close, watch the stars around it without worrying about deadly radiation or jets of plasma. It's the perfect laboratory for understanding black holes, close enough to observe in detail, calm enough to observe safely. One of the strangest things about Sagittarius A star is the region around it, the area within a few light years of the black hole. You'd think it would be empty, a dead zone. Nothing could survive that close to something so massive. But it's not empty, it's full of stars. Young stars, massive stars, stars that shouldn't be there. Stars form in dense clouds of gas and dust. These clouds collapse under their own gravity, fragment, and ignite. The process takes millions of years and requires calm, stable conditions. Near a supermassive black hole, conditions are anything but calm. The gravity is intense, tidal forces are extreme, gas clouds get stretched and torn apart before they can collapse. And yet there are stars there, dozens of them, young, hot, blue stars orbiting within a few light years of Sagittarius A star. How did they form? One theory is that they didn't form there. They formed farther out, in a more stable region, and then migrated inward over time. Gravitational interactions with other stars could have nudged them closer and closer to the black hole. Another theory is that they did form there, but under unusual conditions. Maybe a massive gas cloud, dense enough to resist tidal forces, drifted into the region and collapsed all at once, forming a cluster of stars that still orbit together. We don't know for sure. It's one of the ongoing mysteries. What we do know is that these stars are doomed. Not immediately. Some of them will orbit Sagittarius A star for millions of years, but eventually, gravitational interactions will send some of them too close. And when a star gets too close to a black hole, something called spaghettification happens. The side of the star facing the black hole experiences stronger gravity than the side facing away. The difference in gravitational pull stretches the star, longer and longer, thinner and thinner. Like pulling taffy. Eventually, the star gets torn apart, ripped into streams of gas that spiral into the black hole. This is called a tidal disruption event. We've observed tidal disruption events around other black holes. They're bright, dramatic. They release enormous amounts of energy as the star's material heats up and glows. Sagittarius A star probably experiences these events too, but not often, maybe once every 10,000 to 100,000 years. The last one might have happened long before humans existed. The next one might happen long after we're gone. But it will happen, stars will fall, the black hole will feed. And the cycle continues. One of the stars near Sagittarius A star has a special place in this story. We've already talked about it, S2. S2 isn't just important because it helped prove Sagittarius A star is a black hole. It's also important because it gave us a chance to test one of the most fundamental theories in physics. General relativity. Einstein's theory of general relativity describes how gravity works. It says that massive objects bend space and time around them. The more massive the object, the stronger the bending. Near a supermassive black hole, spacetime is bent to an extreme degree. And S2, orbiting so close to Sagittarius A star, gave scientists a way to test whether Einstein's equations still hold under those conditions. In 2018, S2 made its closest approach to the black hole, periapsis, the point where it's moving fastest and experiencing the strongest gravity. Scientists watched carefully. They measured the star's position, its speed, the color of its light. And they found something remarkable. S2's light was redshifted, stretched to longer wavelengths as it climbed out of the black hole's gravitational well. This is called gravitational redshift. It's a prediction of general relativity. Light loses energy as it escapes from a strong gravitational field, and that loss of energy shows up as a shift toward the red end of the spectrum. The amount of redshift matched Einstein's predictions almost perfectly. They also measured something called the Schwarzschild precession. The orbit of S2 isn't a perfect ellipse. Each time it completes a loop, the orbit shifts slightly, precesses, like a spinning top that wobbles as it turns. This precession is caused by the curvature of spacetime near the black hole. And again, the measurements matched general relativity. Einstein's theory, written more than a century ago, predicted exactly what would happen near a black hole, and S2 confirmed it. But there are still mysteries, things general relativity can't explain. Inside the event horizon, the equations break down. At the singularity, they produce infinities, numbers that don't make sense. This tells us that general relativity, as powerful as it is, isn't the final answer. There's something deeper, some theory that unites gravity with quantum mechanics, a theory we don't have yet. Sagittarius A star might hold clues to that theory. The more we study it, the closer we get to understanding what happens when gravity reaches its limit. And S2 keeps orbiting, 16 years per loop, always returning, always testing the edges of what we know. When you look up at the night sky, you can't see Sagittarius A star, you can't point to it, you can't even see the stars that orbit it. But you can see the constellation Sagittarius, low on the southern horizon if you're in the northern hemisphere, higher up if you're closer to the equator. Sagittarius looks like a teapot, or an archer if you use your imagination, a cluster of stars forming a rough shape against the background of the Milky Way. And somewhere in that direction, 26,000 light-years away, hidden behind clouds of dust, sits the black hole. The thing you're orbiting right now. You can't feel it, you can't sense it. The pull of Earth's gravity is far stronger than the pull of Sagittarius A star at this distance. But it's there, constant, unchanging. Every second, you move 230 kilometers closer to completing your orbit. You've been doing it your entire life. You'll keep doing it until you die. And so will everyone else, every person on Earth, every satellite in orbit, every probe we've sent to the outer planets. All of it circling the same invisible center. It's humbling when you think about it. We spend so much time focused on Earth, on our countries, our cities, our homes. But we're all passengers on a ship moving through space at incredible speed. And the thing steering that ship, the thing holding us in place, is something we only just learned how to photograph. We live in a galaxy, a spiral galaxy, one of hundreds of billions in the observable universe. And at the center of almost every large galaxy, there's a black hole, some smaller than Sagittarius A star, some vastly larger. These black holes didn't just appear randomly. They grew. Over billions of years, they consumed gas and stars and merged with other black holes. And as they grew, they shaped their galaxies. There's a relationship between the mass of a supermassive black hole and the properties of its host galaxy. Bigger black holes tend to sit in bigger galaxies, galaxies with more stars. This isn't a coincidence. The black hole and the galaxy grew together, fed each other, influenced each other's evolution. When a black hole feeds, it releases energy. That energy heats the surrounding gas, and hot gas doesn't collapse to form stars. So the black hole, by feeding, regulates star formation. It controls how fast the galaxy grows. In some galaxies, this feedback is so strong that it shuts down star formation entirely. The galaxy becomes what's called a red and dead galaxy, full of old stars, no new ones being born. The Milky Way isn't like that. Star formation is still happening. New stars are being born in clouds of gas throughout the galaxy. But Sagittarius A star still plays a role. Even though it's quiet, even though it barely feeds, its gravity shapes the region around it. It affects the orbits of nearby stars. It influences the flow of gas. In a way, the black hole and the galaxy are connected, not just physically, but structurally. The galaxy exists because of the black hole, and the black hole exists because of the galaxy. They need each other. And we are part of that system, a tiny part, yes, but part of it nonetheless. The Milky Way will keep evolving. Stars will keep forming. Some will die, explode as supernovae, leave behind neutron stars or smaller black holes. And Sagittarius A star will keep sitting at the center, patient, waiting. Billions of years from now, something will change. The Milky Way is on a collision course with another galaxy, Andromeda, our nearest large neighbor. Right now, Andromeda is about 2.5 million light-years away, but it's moving toward us, and in about 4 to 5 billion years, the two galaxies will collide. It won't be a collision in the traditional sense. Galaxies are mostly empty space. Stars are so far apart that they'll pass by each other without touching. But the gas clouds will collide. They'll compress, heat up, trigger massive bursts of star formation. And the two supermassive black holes, Sagittarius A star and the black hole at the center of Andromeda, will spiral toward each other. Over millions of years, they'll get closer and closer. Their orbits will decay. Gravitational waves will carry energy away. And eventually, they'll merge. Two black holes combining into one, a single, larger black hole at the center of the new galaxy, a galaxy we've already named, Milkomeda. When that happens, the merger will release more energy than 1 trillion supernovae, most of it in the form of gravitational waves, ripples in spacetime itself, spreading outward at the speed of light. By then, Earth will likely be gone. The Sun will have expanded into a red giant, consuming the inner planets. But if any observers remain anywhere in the universe, they'll detect the signal, the fingerprint of two ancient black holes finally coming together after billions of years apart. And the new black hole will settle, calm down, begin its own long wait at the center of the new galaxy. The cycle continues. Sagittarius A star, as it exists now, won't last forever. Nothing does. But in 4 billion years, it will still be here, still pulling, still holding, still anchoring, waiting for its partner to arrive. There's something comforting about Sagittarius A star, something steady. We live in a universe that's constantly changing. Stars are born and die, galaxies collide and merge. The universe itself is expanding, carrying galaxies farther and farther apart. But Sagittarius A star remains a fixed point, a center we can always return to. No matter where you go in the Milky Way, no matter how far you travel, Sagittarius A star will always be there, pulling you, holding you. You can't escape it, and maybe that's okay. Maybe it's good to have something constant, something that doesn't change, even as everything else does. For all of human history, we've looked for centers, places to anchor ourselves, home. And now we know where the center is, not just of our planet or our solar system, but of our entire galaxy. 26,000 light-years away, invisible, silent, but always there. You're still moving, 230 kilometers per second. You've been moving since before you were born. You'll keep moving long after you're gone. Around the same dark center, the same patient pull. Sagittarius A star. The thing at the middle of everything. The thing you'll never see as it is, only as it was. Always late, never now. The quiet giant we're all orbiting. The still point in a turning galaxy. Home. The word black hole wasn't always what we called them. For a long time, we didn't have a name at all. We didn't even know they could exist. The mathematics appeared first. In 1915, when Einstein published his theory of general relativity, a German physicist named Karl Schwarzschild found a solution to Einstein's equations. Schwarzschild was serving in the German army during World War I, stationed on the Russian front. And in his spare time, between battles, he worked through Einstein's mathematics. He found something strange, a prediction hidden in the equations. If you compressed enough mass into a small enough space, you'd create a region where gravity became so strong that nothing could escape, not even light. A boundary would form, a sphere surrounding the collapsed mass. Inside that sphere, all paths lead inward. Outside it, escape is still possible. Schwarzschild calculated the radius of that boundary, the point of no return. We still call it the Schwarzschild radius today. For an object with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. Compress the Sun down to a ball 6 kilometers across, and it becomes a black hole. For Earth, the Schwarzschild radius is about 9 millimeters, less than the width of your thumb. Schwarzschild sent his solution to Einstein. Einstein was impressed, but also troubled. The math worked, the equations were correct, but the results seemed absurd, impossible. Einstein didn't believe black holes could actually exist in nature. The conditions required were too extreme. No physical process could compress matter that much. Schwarzschild died a few months later. Disease. He never saw his solution become reality. For decades, physicists debated whether Schwarzschild's solution was real or just a mathematical curiosity, something that could exist on paper but not in the universe. In the 1930s, a young physicist named Subramanian Chandrasekhar calculated what happens when massive stars die. He found that if a star is massive enough, nothing can stop its collapse. Not heat, not pressure, not any force known to physics. The star collapses inward, past the point where atoms can hold their structure, past the point where even atomic nuclei can resist. It collapses all the way down to a singularity. Chandrasekhar's work suggested that black holes weren't just possible, they were inevitable, the natural end state of the most massive stars. But even then, the term black hole didn't exist. Scientists called them frozen stars or collapsed objects or dark stars. Awkward names, temporary names. The term black hole was coined in 1967 by a physicist named John Wheeler. He was giving a lecture and needed a short, memorable way to describe these objects. Black hole, simple, direct, evocative. The names stuck. And by the 1970s, we'd found evidence that they were real, not just mathematical predictions, not just theoretical possibilities. Real objects out there in the universe. The first candidate was Cygnus X1, an X-ray source in the constellation Cygnus, bright, variable, orbiting an invisible companion. The invisible companion was too massive to be a neutron star, too small to be a normal star. The only explanation that fit was a black hole. And once we found one, we started finding more, dozens, hundreds scattered throughout the galaxy. Small black holes, stellar mass black holes, the remnants of massive stars that exploded and collapsed. But those weren't the only kind. At the centers of galaxies, we found something else, something much larger. Supermassive black holes, millions or billions of times heavier than the Sun. Too large to have formed from a single star, too massive to have grown slowly over time. These black holes must have formed early, in the first billion years after the Big Bang, when the universe was young and chaotic. Exactly how they formed, we still don't fully understand. Maybe they started as smaller black holes that merged together over and over, growing larger with each collision. Maybe they formed directly from the collapse of enormous gas clouds in the early universe. Maybe both processes happened, different black holes forming in different ways. What we do know is that by the time galaxies had fully formed, these supermassive black holes were already there, already anchoring the centers, already shaping the evolution of everything around them. Sagittarius A star is one of these ancient objects, formed billions of years ago, older than our solar system, older than Earth. A remnant from the early universe, still here, still pulling. And we're only just beginning to understand it. When scientists first started tracking stars around Sagittarius A star, they noticed something odd. The stars weren't distributed randomly, they formed a pattern. Most of them orbit in the same plane, like planets in a solar system, all circling in roughly the same flat disk. But a few orbit at wild angles, tilted, perpendicular, almost random. Why? One theory is that there used to be more structure near Sagittarius A star, maybe a disk of gas and dust, similar to the disk that forms planets around young stars. Stars could have formed in that disk, born in a flat configuration, all orbiting in the same direction. But over time, gravitational interactions between the stars scattered some of them, nudged them into different orbits, tilted their paths. Another theory involves something darker. There might be thousands of smaller black holes near Sagittarius A star, stellar mass black holes, the remnants of massive stars that died long ago. These smaller black holes would sink toward the center of the galaxy over time, pulled by Sagittarius A star's gravity. And as they moved through the region, they'd interact with the stars, gravitational slingshots, close passes that fling stars into new orbits. We haven't detected these smaller black holes yet. They're invisible, and unless they're actively feeding, they don't emit radiation. But they might be there, hundreds or thousands of them, lurking in the darkness around Sagittarius A star. An invisible population, shaping the orbits of everything around them. It's one of the many things we still don't know. One of the questions we're still trying to answer. The region within a few light years of Sagittarius A star is one of the strangest places in the galaxy. The gravity is intense, tidal forces are extreme, radiation levels are higher than anywhere else nearby. And yet it's not empty, it's full of activity, stars orbiting, gas clouds drifting, magnetic fields twisting. Scientists have detected filaments near the galactic center, long, thin structures made of ionized gas, stretching for dozens of light years. They glow faintly in radio wavelengths, aligned with the magnetic field, curved and twisted by forces we don't fully understand. Some of these filaments might be connected to Sagittarius A star, shaped by its magnetic field, energized by particles streaming away from the black hole. Others might be unrelated, remnants of old supernova explosions, or structures formed by colliding gas clouds. We don't know. The galactic center is crowded, messy, full of overlapping processes and structures. Untangling what causes what is difficult. But we're learning, slowly, image by image, measurement by measurement. Every observation reveals something new. Every data point refines our understanding. And Sagittarius A star sits at the center of it all, quiet, patient, waiting for us to figure it out. There's a question people sometimes ask, a hypothetical. What would happen if Sagittarius A star suddenly disappeared? If the black hole just vanished, stopped existing? Would the galaxy fall apart? The answer is no, not immediately. The Milky Way is held together by the combined gravity of everything in it, all the stars, all the gas, all the dark matter. Sagittarius A star contributes to that total gravity, but it's only a tiny fraction of the whole. If it disappeared, the galaxy wouldn't notice, not right away. The stars near the galactic center would notice, S2 and the others. Their orbits would change. Without the black hole pulling on them, they'd drift away, fly off in straight lines. But stars farther out, including our sun, would barely feel the difference. Our orbit around the galaxy is determined by all the mass inside our orbital path, hundreds of billions of stars, vast clouds of gas, an enormous halo of dark matter. Sagittarius A star is just one piece of that, a small piece. Remove it and our orbit would change by a tiny amount, so small we probably wouldn't notice for millions of years. But here's the thing, Sagittarius A star can't disappear, not really. Black holes don't just vanish, they can evaporate according to quantum mechanics, slowly radiating away their mass over unimaginable timescales. But for a black hole as massive as Sagittarius A star, that process would take longer than the current age of the universe, trillions upon trillions of years. By the time Sagittarius A star evaporates, the Milky Way will be long gone, merged with Andromeda. The stars will have burned out. The universe will have expanded so much that galaxies will be isolated islands, unable to see each other. Everything we know will have ended. And even then, Sagittarius A star will still be there, fading but present, outlasting everything. So no, Sagittarius A star won't disappear. It's as permanent as anything in the universe can be. A fixture, a constant. The quiet anchor at the center of home. One of the most beautiful things about Sagittarius A star is how ordinary it is. Not in size, not in mass, but in existence. We used to think black holes were rare, exotic, the stuff of science fiction. Now we know they're common. Almost every large galaxy has one at its center. And smaller black holes, the remnants of dead stars, are scattered throughout every galaxy. There might be hundreds of millions of black holes in the Milky Way alone, most of them invisible, silent, doing nothing. Just sitting in the darkness, waiting. Sagittarius A star is special to us because it's ours, because we orbit it, because it's close enough to study. But in the grand scheme of the universe, it's just another black hole, one of countless billions. And that's oddly comforting. We're not special, our galaxy isn't unique, the thing we orbit isn't a rare cosmic wonder. It's normal, common, standard. We live in an ordinary spiral galaxy, orbiting an ordinary supermassive black hole. And that's okay. Maybe it's better this way, better to be part of the pattern, part of the normal flow of the universe. Not an exception, not an outlier. Just one more galaxy, one more black hole, one more group of stars circling endlessly. Part of something larger. There's a kind of peace in that. You're still moving, 230 kilometers per second. The number hasn't changed, won't change, not in your lifetime, not in 1,000 lifetimes. You're caught in an orbit that began before Earth existed, that will continue long after Earth is gone. And there's nothing you can do about it. You can't slow down, can't speed up, can't change direction. You're bound to the path, the long, slow circle around Sagittarius A star. But here's the thing. You don't have to do anything. The orbit takes care of itself. Gravity does the work, you just follow along. No effort required, no choices to make. You're exactly where you're supposed to be, moving exactly as fast as you should. Around the dark center, the invisible anchor. Always circling, never arriving. And maybe that's what orbits are, not destinations, not goals. Just motion, endless, patient motion. Around something you can't see, something you'll never reach. But something that holds you nonetheless. Sagittarius A star doesn't ask anything of you, doesn't require your attention, doesn't need you to understand it. It just pulls, quietly, constantly. And you follow. You've been following your entire life. You'll keep following. Around and around. The long orbit, the patient circle. The thing at the center of everything. Silent. Invisible. Inescapable. The black hole we orbit. The dark heart of home. Always there. Always pulling. Always waiting. Sagittarius A star. The quiet giant. The still point. Home.